Okay, so this is the Chem 100 preparatory chemistry test review. So this is the form 2023 that you should find on Brightspace. Um, so please, I encourage you to take the blank test with a calculator and a crib sheet. Okay, so this is the crib sheet that you get. You should have gotten one, or you should have one. This is the crib sheet that you get. Try it blind, and then come back here and take a look at the questions that you can't figure out. So I'm just going to walk through these. I'm going to break this up into a handful of videos. I think if this thing is like 100 and some odd questions, I'll probably do 30 at a time. And I'm probably going to show one example. And then if it's kind of the same concept, I'll kind of skip over it. But all right, here we go. Okay, so number one, the number one, okay, 1.050 times 10 to the ninth has how many sig figs? All right, when it comes to scientific notation, I don't care about this at all. All I care about is the coefficient. And that's it. How many sig figs does the coefficient have? The coefficient, again, if there is a decimal, as there pretty much always is, we find the first significant figure, the first non-zero, and that and everything after it counts. So in this case, there are 4 significant figures. Every single one of those counts as a significant figure because of the decimal. That takes us to the next question. How many significant figures does the number 0.002100 contain? Again, looking at this number, I'm going to find the first significant figure, or first, or I should say non-zero. Okay, that's the first non-zero. That and everything after it is considered significant. So this case, I have 4 significant figures. These zeros up here are nothing more than just what we call placeholders. Okay, so they just tell you how powerful or what magnitude that 2.2100 is. Also, these zeros at the end, you always often have to ask yourself about a zero is, why would I write those zeros at the end if I did not need them, right? If I didn't need those zeros, if they were not important to report, I would just write that. I would stop there. But the fact that someone put those zeros there says that they're important, okay? Much like if I did something like 2000 and you don't have a decimal, these zeros are just telling you that that 2 is in the thousands place, okay? So this thing, first sig fig, if there's, and the answer always holds true. If there's a decimal, you find your first sig fig, that and everything after it counts as a significant figure. All right. How many significant figures does the difference of this math? So do the math, right? So 218.7201. There's a couple of ways that we can do this. 218.63. So we're going to subtract that. So 218 minus 218, 63 plus 09, right? Yes, there we go. 0901. So that is what the calculator should give you, right? The calculator should give you 0.0901. And now we have to make a decision. So when we add or subtract, we are interested in the place. Really, when there's a decimal, it's actually the number of decimal places, or the least number of least place or least number of decimal places. When we multiply or divide, we are interested in the least number of sig figs. So in this case, when I take a look at this, I can actually create a little line. This is the last sig fig, or I'm sorry, yeah, that's the last sig figs. This goes out to 2 decimals. Okay, so this one right here is 2 decimals. This one goes out to 4 decimals. 2 decimals wins. I'm going to underline the second decimal place, and I'm going to round it to there. So my answer for this whole thing, let me round, is 0.09. That is the answer because I'm rounding to the second decimal place. How many significant figures does this have? I don't care how many sig figs we start with in those numbers. None of that matters. The place is all that matters. One sig fig in this answer. All right. All right. What is the answer follow to the correct number of sig figs? We're going to follow PEMDAS. And this is not going to matter so much for this one, but we're going to follow PEMDAS. That means that we're going to do parentheses. Remember PEMDAS. So parentheses first. Okay. We don't have any parentheses. So we're good. Exponents or roots, we don't have any of those. Multiply and divide, we're going to do multiplication first. So we're really going to do that first. And then add, subtract. There's no add, subtract. We're going to do the 0.09 seconds. So 1.25 times 2.350. The proper way to do this, I put this into the calculator and I ended up with 2.9375. I'm going to leave units out of this. This would be centimeters. Actually, I won't. Centimeters squared. That's everything I got in the calculator, 2.9375. And I'm going to rewrite everything I didn't calculate, okay? Now, while I'm here, I have to decide where I'm going to round. So 1.25, this number has 3 sig figs because according to the last one, remember, we're interested in the number of sig figs because we're multiplying, right? So that has 3 sig figs. This has 4 sig figs. How many sig figs do I round to? Or where would I have rounded if this is the last one? Well, I would have rounded to the 3rd sig fig. So I'm going to underline the 3. That's the 3rd sig fig. Now I'm going to multiply what I had, 2.9375 times 0.9. And I end up with the number 2.64375 centimeters cubed. Again, we don't really care about the unit there. Now let's talk about sig figs. This number has 3 sig figs, right? It would have had, how it's written, it has 5. But where I underlined it, that's where it would have been rounded. So this thing has 3 sig figs. 1, 2, 3 sig figs right there. And the 0.9, that is just 1 sig fig. That means that I'm multiplying again, so I'm interested in the number of sig figs. I am going to underline the first sig fig because I only need to round to 1 sig fig. And now I'm going to round. Interesting. Unless my math is wrong here, and it might be. I end up with a value of, oh, no, we're good. Okay. End up with 3. I thought it was rounding up for some reason. So we're rounding to 1 sig fig. I'm going to round to that 2. That 2 rounds up to 3 because of the 6. The answer is A. Moving on. Suppose a 100 mil graduated cylinder has a mark every 1 mil. Okay, so 100 milliliter graduated cylinder has a mark every mil. That means that if I'm going, let's use that, every mil. So we're going to have these large hashes where we're going to go from 10 to 20. And then we'll have this one, which would be the halfway point, and then 1, 2, 3, 4. So that's kind of what we're looking at. Okay, so every single one of those counts as 1 mil. The halfway hash is 15. There's the other side of it. And the volume level on the graduated for a measured volume is exactly between 15 and 16. Okay, so it's between 15 and 16. Oh, okay. So let me simplify this. Let me change it just a little bit. So I have, we'll just do it like this. Let's say this is 14, this is 15, this is 16, and then we have the measurement. So the number is like halfway between 15 and 16. So when we look at this thing with our eye, what we're seeing is like right there between 15 and 16. Okay, so what I am certain of, what I do absolutely know is that it's above 15. So I can put that in as I know the tens place, I know the ones place because I have the graduation for it. the next one always has to be our guess. So if I have marks every mill, I am guessing the 10th place. I have to make a guess here. So I'm going to call this 15.5 milliliters. Okay. So essentially, you're always going to go one more unit beyond where you have the mark. So if it's in 1 mil increments, you're going to go to the 10th place, right? So in this case, 15.5 is what I'm going to read this thing as, or C. Yeah. So for example, if I had something that read it every, if this were, let's say, yeah. So if this were, let's say 10 and this were 20 and this number were to be here, I only know the tens place. I know it's 10 for certain, it's not 20, but I don't know. This would be 15, I would guess, for this one. Okay, so you always go one beyond what your smallest reading is. That's where your guess is. All right, next up. So let's go to 6. All right, a sample of an element has a mass of 34.261 grams and a volume. Okay, so calculate the density. Density is equal to, D is equal to M over V. So my mass is equal to 34.261 grams divided by 3.8 milliliters. I do not care about the actual answer here. All I'm interested in is the number of sig figs. We're dividing, so we're interested in the number of sig figs. The least number of sig figs. That one has 5 sig figs. And this one has 2 sig figs. So my answer has to be, doesn't matter what it is, it has to be 2 sig figs. Answer is B. Good enough. Moving on. An aluminum sample has a mass of 80.01 and a density of 2.70. According to data, sig figs should be calculated. Okay, so again, D is equal to M over V. Let's rearrange it. I have density and I have mass. So I am going to rearrange this. So I'm going to cross multiply. We can actually just replace volume is equal to mass over density. And you can always switch what's on the top on one side, because this is over 1, with what's on the bottom. So we can just have them switch spots. So I've essentially just said, okay, let's just switch the locations of those two in any event. So I'm going to have a number of 80.01 grams divided by 2.70 grams per centimeters cubed. But none of that matters. We are dividing 4 sig figs, 3 sig figs. So my answer should have, you guessed it, 3 sig figs. Least number of sig figs when we're dividing. All right. How many milliliters is 0.005 liters? Okay, so we're gonna use the numbers that are actually in our crib sheet times fraction. I want liters to go away and I want milliliters to remain. So hopefully you remember this and you don't have to use your crib sheet, but let's use it just in case. So I want to look at what my equivalents are on the table here. So we're given this. And so we're given this column over here. And again, this is the base unit. I'm going to call this the base. So the way that we could look at this is, and this is the prefix. One of the base units, so we'll use meters for example, meters. 1 megameter is equivalent to 10 to the 6th meters. And for milli, 1 millimeter is equal to 10 to the negative 3rd meters. So we can just use this as our conversion. Okay, so 1 nanometer is equivalent to 10 to the negative 9th meters. Okay, so 1 millimeter is equal to 10 to the negative 3rd meters. Okay, so now I'm going to go down and I'm going to plug this in. 1 milliliter is equal to 10 to the negative 3rd liters. Okay, so Now that I plug that in, equals, let's see, liters to mils. So liters is going to cancel, leaving behind 5 milliliters. And we should have 1 sig fig because we started with 1 sig fig. So our answer is going to be 5 mils. Okay. You move the decimal 3 times, but here we are. Okay, how many micrometers in a kilometer? Okay, so the previous one, I went directly from milliliters to liters. So I went to a prefix to a non-prefix. Easy, one step. When I'm going from micrometer, to a kilometer, I always want to go to meters first because you don't, that way you don't need to know those. You can just you can just skip right to that. So 6.0 kilometers times fraction. I need a little more space. I want kilometers to go away. I want meters to remain. And then I'm going to do one more to get rid of the meters and go to micrometers. So we can use the number above. 1 kilometer is equivalent to 10 to the third or 1,000 meters. Okay. One micrometer is 10 to the -6. Again, one of the base units, prefixless units, is equal to, one of the prefix units is equal to whatever the number is next to it of the base prefixless unit. Okay. And there we go. So it looks like, yeah. And so now we just do the math. So pull out your calculator and do the math. So when we plug this into our calculator, you end up with C, 6 times 10 to the 9th micrometers or micrometers. All right. How many nanometers in a centimeter? Same thing. I'm going from a prefix unit to another prefix unit. That means I want to go to meters first. So we're going to do it the same way. We're going to go through meters first. The answer for this one should be A. All right. So next up, again, using the numbers from above. All right. An aluminum beverage can contains 12 fluid ounces. Express this volume as microliters. Okay, so we are looking for microliters. So in order to get that, first thing we need to do is we need to see what conversion we have. So we have ounces to milliliters. Okay, we can deal with that. So step 1, we always write the original number that we have, fluid ounces. And I know I want that to go away, so I'm going to put that at the bottom. Myself a little more room. There we go. And I want to go to milliliters. So 1 fluid ounce is equivalent to 29.6 milliliters. At this point, fluid ounces cancels. The next step is let's get rid of milliliters. Do you know how many milliliters are in a microliter? We don't. So we can just simply go to liters. 1 milliliter is equal to 10 to the -3rd liters. Again, we're looking at I'm using the thing above. Milliliters cancels. Next up, I want liters to go away, and I want microliters to remain. 1 microliter is 10 to the -6th liters. Liters cancels, and I'm left with milliliters. It was a trip to get there, but that's what you get. And off we go. So 12. See, 11. So the answer for this should be 3.5 or 3.6 times 10 to the 5th. So there we go. All right, good. Moving on. Let's take a look at 12. Which statement describes the charge of an electron, the charge of a proton? All right, so let's just make a quick little table. We have 3 subatomic particles. We have a proton, we have a neutron, and we have an electron. So I want to talk about 2 things when it comes to these. And we don't really care about the actual numbers associated with this. What I really care about is, all right, the relative numbers. So what I'm interested in is the charge relative charge and relative mass. A proton has a positive 1 charge. A neutron is neutral. And an electron has a -1 charge. There is a good balance there. It turns out that the way an atom looks is all of the things in the nucleus are made up of protons and neutrons. So they both have a mass. So protons and neutrons in the nucleus. And around the outside, we have electrons, which actually have very little mass. They actually have 1/1000th the mass of a proton, so they really don't matter in terms of total mass. So the relative mass of a proton is 1, the relative mass of a neutron is 1. So there's a good symmetry here. Protons and neutrons make up all the mass. Protons and electrons are the things that balance charge, okay? So which statement describes the charge of an electron and the charge of a proton? So an electron and a proton both have +1 charge, -1 charge. That's just not true. An electron has a charge of +1, not true. An electron has a charge of -1, yep. And a proton has a charge of +1. Great. Answer is D. So that's it. We have to remember that all of the mass is in the nucleus. The negative charge from the electron balances out the number of protons in the nucleus. So which describes the location of protons and neutrons in the atom? Protons and neutrons are in the nucleus. That is true. Protons and neutrons are outside. Nope, that's where the electrons are. Protons are outside the nucleus and neutrons, nope, those are in the nucleus. Protons are in the nucleus, nope. Yeah, so protons and neutrons are in the nucleus and the electrons are orbiting outside. Which term is defined as the region in an atom where an electron is most likely to be located? Okay, so they're definitely not in the nucleus because that's where the protons and neutrons are. We're not going to deal with words like quanta. Definitely in an orbital, they're orbiting the center of the atom, okay? And spectra is typically the stuff that we collect when we have data, but an orbital is where, so if this is the nucleus, the electrons are cruising around the outside in an orbital. Which particle has the least mass? Okay, proton, 1 AMU. Electron, 0 AMU. Neutron, 1 AMU. And a hydrogen atom, which is made up of just a proton, really, 1 AMU. So an electron, no mass, 1/1000th of a nucleus, or a proton. Which statement describes two different isotopes of carbon? An isotope is the same mass, or I'm sorry, same element, which means that's the equal protons, different mass. So not equal or more or fewer neutrons are different. All right. An isotope contains the same number of neutrons. No. Isotope contains the same number of neutrons. Nope. The isotope contains a different number of neutrons. Okay, yes. But have the same atomic number. Absolutely. Same atomic number equals same element. And it's not that. Yep, there we go. All right, moving on. What is the number of electrons in a neutral atom that has 20 protons and 17 neutrons? Okay, so let's just name this whole thing here. Okay, so if we look at the periodic table, all right, 20 protons, element 20 is calcium. So calcium is element 20. So that is where we're going to see the number of protons. The number of neutrons is 17. If I add these two things together, I have a mass of 37. That right there is the combination of neutrons and protons. Okay, so the mass is both of those. Up here in this corner is where I would find the charge. do I have an excess of positive or negative? So do I have extra electrons or extra protons? I don't, right? There's no mention of charge. So we're going to assume that this is neutral. So it is usually proton. It is not usually. It always is. Protons minus electrons. That's how you determine charge, or positive minus the negative total to give you the actual charge. So if I have 20 positives in this case, minus the 20 negatives, we're going to have a 0 charge. So how many electrons do we have in a neutral atom? You have an equal amount. All phosphorus atoms, okay, phosphorus. If it's phosphorus, that is element 15. That is the same atomic number, which is 15 for phosphorus. The mass number can change. That would make an isotope. Number of neutrons and electrons, it can be an ion, so it can have extra electrons or not. Number of neutrons and protons, that's mass. So that's the same thing as mass, right? So atomic number, number of protons, that's what's the same for phosphorus. An atom that contains 6 protons. So right away, I know it has 6 protons, and I know looking at the periodic table that that's carbon. 6 neutrons, so 6 protons and 6 neutrons makes carbon 12. We're going to put the mass up in that corner. And 6 electrons. So 6 electrons, the charge is 0 because 6 positives, right? So 6 protons, 6 positives, which is protons, plus the 6 negatives together, that gives us a 0 charge. Okay. An atom that contains 6 protons, 6 neutrons, what's the mass, the approximate mass? Well, there's the mass, the neutrons and the electrons. So it has an approximate mass of 12. Compared to an atom of C12, an atom of C14. Okay, so C12, because they're both carbon, they have the same number of protons. So a greater, so what's different about them? That's really what this question's asking. The protons are the same. And because they're both neutrons, the electrons are the same as well. So they both have 6 plus, they also have 6 minus. Okay, the atomic number is the same thing, right? So the weight here, anytime you have a different mass, you have an isotope, you have to have the only thing you have is a different number of neutrons or a different mass. What is the charge of an ion that has 12 protons? All right, so I've got 12 positive charges and I have 10 negative charges, okay? We don't really care about that because all it's asking about is charge. So if I were to look at this in terms of what's going to happen, I would have 2 positives left over, okay? And that's what the charge is going to be. So 10 of the negative charges cancel out all but 2 of the remaining positives. So a +2 charge is what we should end up with here. An oxide form, okay, so this right here, atomic number is 8, so there's my protons. 16 minus 8 gives me 8. That's the number of neutrons. So thinking about charge of 2 minus. So if it has 8 positive charges, let's say if it had 8 negative charges, it would be neutral, but it has a -2 charge. We never can't change the protons, but we can change the electrons. It has 10 electrons. So I have 2 extra electrons present, making this negative. So 8 protons, there we go. And 8 neutrons, okay, so both those work. 10 electrons, D. A would be a neutral oxygen. All right, good. Let's see here. I think we'll get through the next page and that'll be it for this video, which is 33. All right, an aluminum ion, Al3+. Okay, so in terms of making ions, just remember this. I'm positive. I lost an electron. So the way that we remember this is if it's a positive charge, you always lose that number of electrons from the neutral atom. So a neutral aluminum. Okay, so a neutral aluminum has 13 protons or 13 positive charges. Okay, if I change to aluminum 3+, So this would have 13 electrons too, which is negative. I'm positive I lost an electron. So it's still aluminum, so it has 13 protons still. But it lost how many? Well, the charge is 3 plus, so it lost 3 electrons. 3 minus 10 gives me a plus 3 charge. So 13 protons can eliminate those, and 10 electrons is going to answer as B. All right, which list represents the classification of elements? Nitrogen, neon, magnesium, silicon. Okay, so we're going to need our periodic table for this, so let's take a look. Your periodic table is broken into really 2 parts. So first of all, let's put the little staircase in. I know aluminum is a metal, and so I'm going to start the staircase above aluminum because boron is not. Silicon is what we call a metalloid. It's what we use. It's a semiconductor. It's what we use for. It's a semi-metal. It's partially a metal. Okay, so we're going to do this. The staircase always starts above aluminum and it works its way down. We start a lot of things. Fixed charge also starts at aluminum. So aluminum is important in our calculations here. On the left side, these over here are all metals. These here are non-metals. In terms of the periodic table, boron above the line, aluminum is the only exception to this. Okay. And then everything else that's on the staircase here is going to be considered a semi-metal. Okay, we're never going to make it all the way down here to the right, but silicon, germanium, SiGeAs, Sb, Te, all of those are considered metalloids or semi-metals. So anything up here, non-metal, anything here is a metal, anything that's yellow is what we call a semi-metal. So let's go back to our question. All right. List them as, here we go. Nitrogen. Nitrogen is a non-metal. It's nitrogen comes in the form of a gas, right? It's not lustrous. It doesn't act like that. So that's a non-metal. So I can immediately eliminate those 2. Neon. This is actually a noble gas. Noble gases are in the last row. So they're the ones that are the most stable. They're in group 18. So we can eliminate this. Next, magnesium is a metal. Yep, that still checks out. And silicon is a semi-metal or a metalloid. So there we go. B is the answer. Which of these contains a metalloid, and a non-metal? So I'm going to let you do that one. Yeah, I'm going to let you do that one. All right. A compound is a substance composed of 2 or more elements that are, okay. A compound is, let's use H2O as the example. They are fixed. Every single water has 2 hydrogens and 1 oxygen. So they are going to have a fixed proportion. So I'm going to eliminate B and D because they're never variable. Water is always going to be 2 hydrogens, 1 oxygen. And they're chemically mixed. I'm not mixing together hydrogen and oxygen to make it. They are chemically combined, right? These 2 things combine together to give me water. Which type of matter cannot be broken down into similar substances by chemical change? Okay, any things that cannot be broken down by chemical change are the simplest version of something that we have, which is an element. Because I can take water and I can hit it with electricity and I can break it into its elements. So I go from a compound to elements. Okay, so I can break it down chemically. I can go from a compound to elements. There we go. All right. Oh. All right. So element. Yeah. Chemical change. A physical change allows me to separate a mixture into pure substances, but that's what we're looking at. All right. 2 grams of potassium chloride are completely dissolved in a sample of water in a beaker. This solution is classified as, okay, so I have a thing of water. Right away in here, I have water. So that in itself is a compound. Then I'm going to add in KCl, which is potassium chloride, also a compound, okay? When they mix together, I have a homogeneous mixture or a solution of KCl and water. I have two compounds together. We call this a homogeneous mixture. It would be heterogeneous if the salt did not dissolve, but the fact that it dissolves that it's homogeneous. You can see there's visually indistinguishable. The potassium chloride in the top is the same as it is in the bottom. All right, moving on. All right, so let's take a look at which substance cannot be broken down by chemical change. Again, what can't be broken down? Elements can't be broken down any further. Which sample of matter represents a mixture? Aqueous ammonia. That right there means it's dissolved in water. There's our answer. Gaseous ethane. Okay, so gaseous ethane basically means it's just that. Liquid mercury. This is an element. Solid iodine. Doesn't matter solid, liquid, or gas. Aqueous indicates it is dissolved in water. Okay, all right. Given this diagram, which type of matter represented by that diagram? This right here, they're all the same, okay? Every single one of these is the same. These are all compounds. And because that box has all the same compounds, it's not an element because we don't have one sphere present. It's not a mixture because I don't have anything other than just that one compound. So we're going to call that just a compound. If all of those were black or white only, that would be an element, okay? If they were split up into black and white, we would call that a homogeneous mixture. All right. Which particle represents a mixture of three substances? All right, I'm going to highlight them. So black, white, black, white, black, white. Okay, there's one compound there. The pink one there is an element. There's only two pure substances in that one, so that's not right. Element, element. The two black ones count as elements as well. And this is a compound. So right there, that looks like that is three. That looks like that is three things, three substances. Let's just finish up here. Let's see. I'll just keep the color codes the same. Element, element, element. Compound, compound, compound. So we have a new compound here. And then the last one, compound, 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 and element. So in the end, there are two different things here. There are three here. We only have two here and two here. Okay. All right. Which process is a chemical change? Okay, evaporation. Evaporation. So what we're looking for, physical chemical change is something that is happening that is going to destroy the substance. But we also want to look for a physical change and eliminate those. Physical change is just going from one phase to another. So either going from solid to liquid to gas, or the other way, from liquid to solid, or gas to liquid, or gas to solid, or solid to gas. Any of those count as just simply a physical change. So I'm just going to eliminate those. Evaporating. Okay, so evaporating is going from liquid to gas. That is a physical change. Subliming, that is going from solid to gas, eliminating that. Melting, that is going from solid to liquid, eliminate that. Rusting, that is chemically changing. It's no longer iron, it's an iron oxide substance. It's not the same as it once was. Okay, so that's up to 33. More to come.